Hello, and welcome to Lesson 4 of this Introduction to Differential Equations with Wolfram U. We have now introduced the concept of differential equations, direction fields, and how to obtain a solution to certain types of differential equations. Before we proceed with discussing solution methods, we should take a moment to discuss how to classify a differential equation. Let's take a look at an overview of this lesson. Differential equations can take many forms and include functions of many variables. The first equation here is an instance where we have one dependent variable and one independent variable, while the second equation is an example of a differential equation where there are two independent variables, x and t. In this lesson, we will discuss the methods of defining, solving, and plotting general differential equations in the Wolfram language. The graph here is a guide for how one can classify a differential equation. We can first classify the equation as an ordinary differential equation, such as the first equation up here, or as a partial differential equation, such as the second equation. We can then classify the equations as linear or nonlinear, homogeneous or non-homogeneous, and so on. We'll define these terms in this lesson. The first type of equation we will consider is an ordinary differential equation, or an ODE. These are differential equations in which only ordinary derivatives appear in the differential equation, and the unknown function depends only on a single independent variable. Here are three examples of ordinary differential equations. In the Wolfram language, we can obtain symbolic solutions to many differential equations with the dsolve value function. The first argument of dsolve value is a list containing the differential equation being solved, along with any initial conditions that may be present. The second argument specifies the dependent variable in the differential equation, while the third argument defines the independent variable. We will begin with an initial value problem for an ordinary differential equation. The differential equation is given here, where the second derivative of the solution appears in the equation. The initial conditions are saying that the value of the solution equals 0 at x equals 0, while the first derivative of the solution equals 5 at x equals 0. It is the inclusion of the initial condition that makes this an initial value problem. Now that we have the differential equation and a set of initial conditions, we can easily obtain a solution using dsolve value. The solution to the differential equation is now stored in the variable sln. This makes it particularly easy to visualize the solution using plot. It is always important to verify a solution by substituting it back into the differential equation. We can see that the solution we found to this initial value problem does satisfy the differential equation. Let's now consider the initial value problem here, where the differential equation now includes an f of x term on the right-hand side, while the initial conditions are the same as in the previous example. Using dsolve value with the equation and initial conditions in the list in the first argument, we can calculate the solution to this initial value problem very easily. As was the case before, since we saved the solution in the variable sln, we can simply apply the plot function to visualize the solution. Substituting the solution we found into the differential equation shows that it does satisfy the equation. With partial differential equations, or PDEs, partial derivatives rather than ordinary derivatives appear in the equation. In such a case, the unknown function will depend on multiple independent variables. Here are three examples of partial differential equations. Notice that in each PDE, the unknown functions have two independent variables, while partial derivatives or even mixed partial derivatives with respect to these independent variables appear in the equation. Dsolve value can be used to solve many types of partial differential equations. However, the theory of partial differential equations is not as well understood as that of ordinary differential equations, and will thus play a minor role in this course. Let's take a look at solving an initial value problem involving a partial differential equation. The PDE here has the u function as the dependent variable, with x and t being the independent variables. The initial condition is saying that at t equals 0, the solution equals sine of x for all values of x, while at x equals 0, the solution equals 0 for all values of t. When writing initial conditions to PDEs, it is important to make sure that the conditions are consistent. For example, when x and t are both 0, we get a condition on u at t equals 0 and x equals 0. Both initial conditions make a statement about this location, so they should agree at that point. The conditions in this case are consistent. Since sine of 0 is equal to 0, the first condition is saying that the u function at t equals 0 and x equals 0 should equal 0, which is also what the second initial condition is saying. Now, to solve this equation in the Wolfram language, we need to first define the equation. Then we need to define the set of initial conditions and boundary conditions. With the equation and conditions defined, we can use dsolve value to solve a PDE in the exact same way we use the function to solve an ODE. In the first argument is the list containing the equation and conditions. The second argument is the dependent variable, while the last argument is the list of independent variables. Since the solution depends on two independent variables, we need to use plot3D to visualize the solution. The order of a differential equation is the order of the highest derivative that appears in the equation. For example, this here is a second-order differential equation because the second-order derivative term is the highest-order derivative. The derivatives can easily be calculated in the Wolfram language using the prime notation. The next differential equation is a fifth-order differential equation. Using the superscript of 5 in parentheses is common notation to represent higher-order derivatives to make the order of such derivatives more clear. When very high derivatives are present, it may sometimes be more convenient to use the Wolfram language d function to calculate the derivatives instead. An ordinary differential equation is said to be linear if it can be written in the form here. In this equation, the a of t and g of t functions are arbitrary differentiable functions that do not need to be linear. The main point with linear equations is that there are no terms involving the product of derivative terms, and the terms involving the dependent variable are not raised any powers. The mathematical theory and methods for solving linear equations are highly developed and will be the main focus of this course. An ordinary differential equation is said to be nonlinear if it cannot be written in linear form. For example, these are two linear differential equations, since their derivatives all appear in separate terms, and none of the dependent variables are raised to any powers. However, these are examples of nonlinear differential equations. The first equation is nonlinear for two reasons. The first is the product of the second derivative and the first derivative, and the other is the y of t term is squared. The second equation is nonlinear because of the square root of the first derivative term. As stated on the previous slide, an ordinary differential equation is said to be linear if it can be written in this form. When the g of t term is equal to 0, the differential equation is said to be homogeneous. For example, this is a linear homogeneous differential equation. When each of the a of t coefficients are a constant scalar, the equation is said to have constant coefficients. The class of differential equations that are most understood is linear homogeneous differential equations with constant coefficients. Now that we have introduced a lot of terminology in a short period of time, let's take a look at a few examples of classifying differential equations. The first equation here is a first-order homogeneous linear equation with constant coefficients. It is first-order because the highest-order derivative is a first-order derivative, while it is homogeneous because there is no g of t term, which would be a term that depends only on t and not on the dependent variable. You can use Wolfram alpha to check the classification of a particular differential equation. The second argument in the Wolfram alpha call is selecting just the part of the Wolfram alpha output that we are interested in. Considering this differential equation here, we can see that it is a second-order non-homogeneous differential equation, where sine of x is the non-homogeneous term. Once again, we can use Wolfram alpha to verify this classification. Next, we have the differential equation here. We can see that this differential equation is a nonlinear equation. It is nonlinear because of the product of the second derivative of y with y of t. Wolfram alpha again confirms this identification. Let's now consider the differential equation here. This is a second-order, non-homogeneous differential equation when the function e of t is not equal to 0. Checking with Wolfram alpha confirms this classification. Finally, we have a second-order, homogeneous, nonlinear equation. It is nonlinear because the second derivative is raised to the fifth power, and it is homogeneous because there is no g of t term that would depend only on t and not on the dependent variable. Wolfram alpha once again confirms this to be a nonlinear equation. In this lesson, we reviewed some of the important concepts when classifying differential equations. We saw that in an ordinary differential equation, the unknown function depends on a single variable and only ordinary derivatives appear in the equation. The order of a differential equation was seen to be the highest derivative that appears in the differential equation. We learned that an ordinary differential equation is said to be linear if it can be written in this form, while the equation is said to be homogeneous if the g of t term is 0 and non-homogeneous otherwise. Ordinary differential equations that are homogeneous, linear, and have constant coefficients are the most understood class of equations and will be our topic of study shortly. The graph here summarizes the various classifications for differential equations we discussed in this lesson.